Hello, in this video I'd like to talk about monoids. So a key concept in model theory is that of a structure, a collection of objects and things that we can do with those objects. So things like operations, functions, or predicates and relations. And we also might want to have some distinguished constants that we can talk about as well. And structures are really important because they allow us to focus our attention on a very small subset of mathematics. And this is really important for model theory. Model theory is interested in structures and languages. And if we're going to be talking about languages, well, mathematics as a whole is this gigantic language. It's very open-ended. People are adding to it all the time. But if we focus our attention down on some very small portion of mathematics, suddenly the language becomes bounded. And because it's a formal language and it's bounded, we can reason about all of the things that we can say in that particular language. We can formally reason about everything that we can say in this language has to be constructed in this particular way. It has to be some sort of formula that's generated in a particular fashion. And again, we can only do that because we're focusing on some very limited subset of mathematics, and that's what structures are about. Structures are very similar to classes in object-oriented programming. So some classes are kind of built in. They're things that we already know about, right? We already know about integers, we already know about real numbers, we already know how to add and multiply them, for instance. But you can also create your own classes. Suppose that you want to create a quaternion class and there's no quaternion class already in your programming language. Well, then you can do this. You just define this new thing, you define what it means to be a quaternion, and then you define how to add and multiply them. And it's the same thing you do in mathematics. When you're creating a new type of structure, you define what it means to be that thing, although it doesn't have to be programmatic anymore. And then you define what it means to add or multiply those things, or whatever operations, whatever things you want to be able to do with the elements of that structure. And then you can just define whatever sorts of structures you want. And a useful notation for this is equipment notation. We talk about, let's say that we wanted to talk about real numbers. So we use the notation for the real numbers, this math blackboard bold R. And then let's say we wanted to talk about addition, subtraction, and multiplication, but maybe we won't talk about division of real numbers. And then we'll also want to be able to talk about some constants like 0 and 1. And then let's say that we also want to talk about less than or equal to. And that's it. So this here is a structure. It's the real numbers equipped with addition, subtraction, multiplication, constants 0, 1, and less than or equal to. And we can study its properties. And when we're studying the properties of this, we're specifically excluding other things from our consideration. For instance, nowhere here do you see the integers. So if we're going to talk about integers when we're reasoning about this structure, we need to somehow be able to maybe define the integers within this structure. Otherwise, we aren't concerned about integers. Similarly, we don't need to worry about the properties of trig functions or logarithms because nowhere here have I specified those. When we're writing programs that use elements of our classes, it's really important to know what sorts of properties, what sorts of algebraic properties are true of those objects. So for instance, we want to know, is A times B equal to B times A? Do we need to worry about the order that we multiply things in when we're writing our code? If we do, then it's really important to check every time you multiply things and make sure that you're multiplying them in the right order. And if not, well, it's not important to do that at all. We don't need to worry about doing that check. And whether or not this is true really depends on the type of structure that we're looking at. If we're looking at this structure up here, sure, it's true. Multiplication of real numbers is commutative. On the other hand, if we're talking about multiplication of quaternions or multiplication of matrices, this isn't true. When you're writing programs that involve matrices and involve multiplication, you need to worry about the order that you multiply those matrices in. And knowing what sorts of rules are available is even more important in mathematical algebra, because, I mean, that's essentially what you're doing. You have algebraic formulas and you're allowed to rewrite them, but you're only allowed to use valid rewriting rules. Rewriting rules that commonly occur together are oftentimes given a name. For instance, anything that satisfies all of these rewriting rules is called a ring. Rings are a class of structure, along with fields, groups, linear orderings, and vector spaces. Classes of structures are defined by a combination of templates, what sorts of operations, relations, and constants we can expect this structure to have, and rules that these structures are required to satisfy. Closely related to model theory is the study of abstract algebra, which focuses on these sorts of structures, specifically groups, rings, and fields, with the goal, for instance, of proving something for all rings at once, or all rings of a certain sort, or all groups, or all fields. So while the algebra that you may have taken earlier in your mathematical career focused just on the rewriting rules and the properties of the real numbers, abstract algebra seeks to prove something for every single ring at once. And so once you prove something, not only do you know that it's true for the real numbers, but you also know, for instance, that it's true for the n by n matrices. And the valuable thing that I take away from that is the study of how these various rewriting rules are related to each other. So while your earlier algebra focused on just the rewriting rules for just the reals, abstract algebra focuses on a more abstract study of rewriting rules. And also solving polynomial equations, it turns out that's really popular. So monoids are a fairly simple class of structure, which consist of just a set of elements, a binary operation on that set of elements, which I'm going to use multiplication notation for, not because, I mean, it's close to multiplication in terms of its properties, but just because it's really convenient. We have this very nice notation where we put things next to each other to indicate multiplication, and I want to be able to use that. And we need to have a special constant element, which I'm just going to call E. So this is our template. We have our set of elements. We have a binary operation on that set of elements, and we have a constant element of that set of elements. And the rules that we're required to satisfy look like, if we have two elements of our structure, then their product is also an element of that structure. This is called closure. And we also have associativity. So if we have three elements of our structure, then A dot B dot C is equal to A dot B dot C. And this is a really important property of any sort of algebraic structure, because if you don't have this property, then whenever you want to write down a formula, whenever you want to write down an algebraic expression involving these variables, you have to put parentheses to indicate whether you mean this or this, if they're not necessarily going to be equal to each other. So it's really useful to have this be equal to this, because that lets us use the notation A dot B dot C unambiguously, and it means that we don't have to count parentheses. We don't have these formulas that just have tons and tons of parentheses in them, and we have to make sure that we've written them out correctly. And then finally we have the property that if A is an element of our structure, then A dot E is equal to E dot A is equal to just A. This property is called identity. It's the property that 0 has when it comes to addition, and the property that 1 has when it comes to multiplication. So let's talk about some examples of monoids. For instance, addition very often satisfies these monoid properties. We could talk about addition of the integers or addition of the natural numbers. We just have to make sure that we have closure. Addition is going to satisfy associativity, and addition is going to satisfy identity, provided that this 0 is actually part of our set. So for instance, you can't say the odd numbers form a monoid under addition because they don't have zero. I mean, zero exists, but it isn't in the collection. It has to be in the collection. We also have multiplication of the positive integers or multiplication of the non-zero integers. Many other binary operations, such as union and intersection, satisfy associativity. And so, for instance, if we're looking at the subsets of a given set, then those form a monoid under both the union and intersection properties. And it's always valuable to think about this, to check to make sure these properties are satisfied, and to try to figure out what is the identity element when we're talking about union and intersection of subsets of a given set. If we have a particular set, functions from that set to itself under function composition are going to form a monoid. Function composition is associative. I'll let you check that. And this is actually one of the key monoids to help get you intuition for how monoids work. The n by n matrices form a monoid under matrix multiplication. And most relevantly for us, words under concatenation form a monoid. So I'll let you think for a moment. What is the identity element when we're thinking about words under concatenation? Here I'm going to use the superscript frown notation for concatenation, just to make it clear that I'm talking about concatenation. And our identity element is the empty string. So this here is a monoid. This monoid is said to be generated by the letters of this particular alphabet, because any element of this structure, any word on this particular alphabet, can be put together by just taking the letters of the alphabet and concatenating them together a whole bunch. So we say that this is generated by the alphabet, by the individual letters. And what's more, we actually say that it's freely generated, which just means that when we combine a bunch of things together, we don't get any non-trivial identities, right? When I combine a whole bunch of letters together and combine a different collection of letters together under concatenation, I'm not going to wind up getting the same thing, even though I used completely different basic letters or combined them in a different order. I'm only going to get the same thing if I concatenate the same letters in the same order. There are some structures, for instance, matrices. If you multiply one set of matrices together and you multiply another set of matrices together, you might wind up getting the same matrix, even though it wasn't obvious at all that you were going to get that. You weren't multiplying the same things in the same order. And so that wouldn't be freely generated. But this set, the set of words, is freely generated by sigma, because anytime you combine together basic letters, the only way to get the same thing is to combine things together in the same way. So this is actually a really important monoid as far as monoids go. So monoids are just one of a wide variety of classes of structures that we could be studying. Depending on what field of mathematics you're studying, you could be interested in adding more rules to what it means to be a monoid, to get some sort of more structured sort of object. For instance, perhaps the most commonly studied object of this sort is a group, which is just a monoid where we've added in the ability to invert any element, an axiom that looks like this. On the other hand, we might be interested in eliminating some requirements. For instance, if we take the definition of a monoid and remove the requirement that there be an identity element, because we don't always have an identity element, but we still keep the associativity property, we get what's called a semigroup. And in fact, we could eliminate all of our requirements except that our operation be closed and get what's called a magma. I've put together a chart of a wide variety of structures that look kind of like monoids, that they have some sort of set and some sort of binary operation on that set. And again, depending on what you're studying, different things might be the right things to study. It turns out that monoids are the right thing to study when we're studying finite state automata. But first, let's take a moment to have an important insight about rewriting rules and how we can capture those. If we're really interested in capturing the use of rewriting rules in various common mathematical structures, we're going to want to allow our structures to have different kinds of variables. For instance, when we're trying to write out all of the rules of what it means to be a vector space, we're going to want two different kinds of variables. One kind of variable representing vectors and another kind of variable representing scalars. And so it makes sense that we're going to want to be able to talk about structures that have more than one different kind of element. A monoid action is going to be a monoid together with a separate set of elements that our monoid is going to act like functions acting on that set. And we're going to want to add in a notion of multiplication that's really kind of like function application. For this, I'm going to use a large dot to distinguish it from multiplication within the monoid. But once we can tell the difference between elements of our set and elements of our monoid, it's going to be clear which type of multiplication we're referring to. This type of multiplication takes in two elements of our monoid and spits out an element of our monoid. This notion of multiplication, however, takes an element of our set and an element of our monoid in that order and outputs an element of our set. And to be able to tell the difference between elements of our monoid and elements of our set, I'm going to use capital letters for elements of our set, which is actually a little bit weird. Typically you want capital letters for sets, but we have to use some sort of notation, and I'm going to use this one. So what we're really looking at is a structure that has two different types of elements. We could write this in equipment notation as having both a set of elements of our monoid and a set of elements that are getting acted on by our monoid. And then we have two notions of multiplication. One notion of multiplication which is just among elements of the monoid, and then this other notion of multiplication which combines elements of our set and elements of our monoid. So these are fundamentally different sorts of things, which I guess we should indicate somewhere, but I'm not exactly sure where we can indicate that. And then finally, we of course have our identity element of the original monoid. And the rules for this structure, in addition to the basic rules for what it means to be a monoid, are going to be that the identity element of the monoid acts like the identity function on the set if we apply e to an element of S, call it capital X, we're just going to get back that capital X element. And a compatibility property, which really looks like associativity. And it's worth checking that this equation here makes sense, that it types correctly. What we have on this left-hand side, we have the monoid product of two elements of the monoid. So this is going to be an element of the monoid. And then when we take an element of our set and big multiply it by an element of our monoid, we get an element of our set. So the left-hand side represents an element of S. And then on the right-hand side, here we have an element of S, big multiplied by an element of the monoid to give us an element of S, big multiplied by another element of the monoid to give us an element of S. So this is an equality between two different elements of S, and it's just saying that the monoid operation acts kind of like function composition. If we're viewing these elements of the monoid as functions, this is function composition, right? If we take x and we apply m to it and then apply n to it, that's the same as applying m of n to x. And I flip things around. Normally you'll see the elements of the monoid on the left and elements of the set on the right to look more like function notation, but function notation is bad. Function composition is backwards. So I wanted to use a more sensible notation in defining what it means to be a monoid action. So all in all, the template and the rules for a monoid action look like this in total. So this is all very abstract. What does it have to do with finite state automata? Well, suppose that we have a deterministic finite state automaton. This gives us an action of sigma star, the monoid of words under concatenation, on the alphabet of the finite state automaton, this gives us an action of this monoid on the set of states. Specifically, given a word and a state, we simply imagine what would happen if the finite state automaton was in that state and we typed in this word character by character. That's going to give us a new state, and that's going to be the output of this operation. So let's check these two properties. We already know that sigma star is a monoid, that words under concatenation form a monoid. All we need to do is check that if we have a particular state and we apply the identity element of our monoid, that is the empty word, to that state, then we get back the state that we started in. Well, that's exactly what happens. If I have a finite state automaton and it's in a particular state, and I type in all of the characters of the empty word, which is none of them, then when I'm done doing that, the automaton will be in the state that it started out in. So this is going to be true. This identity property is going to be true for this particular monoid action. Additionally, if we're in a state and we apply the concatenation of two words, that's the same as applying the first word and then taking the result and applying the second word. So this operation here that we defined really does satisfy the property of being a monoid action. So this is all very abstract, and it uses a lot of technical jargon to describe what's really a simple idea. This idea of if we're in a state and we type in a particular word, what state are we going to wind up in? And part of this is gatekeeping, but most of it is trying to form connections between lots of very different things that all wind up being instances of this particular type of structure. All of the monoid actions are related by the fact that they're monoid actions, including this one. And so it becomes really natural to make connections between these sorts of monoid actions and other sorts of monoid actions. This sort of obfuscating but unifying jargon shows up in all sorts of branches of mathematics, including algebra, and so it's often very valuable to take a step back when you're looking at something very abstract and try to understand what it means for your very concrete case. In this case, this very abstract property here meant something very concrete, that if we concatenate two words together and apply it to a state, that's going to be the same as applying the first word to the state and then applying the second word to the state. Very simple concept in an abstract but also unifying notation. So far in this series of videos, we've been really interested in finding lots of different ways of characterizing the regular languages. And in this sort of notation, we can describe the regular languages as the set of all words such that that word applied to some specific element is in some subset of our set for some element of a set, for some subset of that set, and for some monoid action of sigma star on this finite set of states. In other words, once we have this monoid action of sigma star on our finite set, all we need is a starting state and a set of accept states, and this gives us a regular language. So thanks for watching, and I hope to see you in a future video.